This will be the first in our speed calculation project pack. You've got a total of 5, and they're all reasonably similar, so let's work through project number 1 together so you can get a sense of the flow in the way that we're looking to get this done. Before we look at the data sheet, I want to talk about some terminology that we use. And this was some terms, breakpoint, that was used in the parts and pieces and the brake discussion. And the bottom line for this is that traditionally, steer axles don't lock up, so you're less likely to get measurable evidence from the steer axle. As long as everything is working well, that's going to be the case. But we can get measurable evidence from the drive axles and from the trailer axles. And as you're working through your evidence field out on the scene, you may see a tandem tire mark that you know is related to this crash. And if your truck's not sitting right on top of those marks, for instance, skidded to a stop and then pulled to the side, you're going to look at that and say, okay, I can look at the evidence, the nature of the tire mark. I can look at the construct of these tires and see maybe the drives have got lug tires on it where the trailers have ribs, and I can say reasonably certainly, for instance, that a particular set of marks belongs to the left side of the trailer. But oftentimes, trying to decide if it came from the front axle of the trailer, from the rear axle of the trailer, can be a little bit more difficult. So we're just going to use those axle groupings and just call them breakpoints. So, for instance, I had some evidence that indicated it was from the left side of the trailer. I'm just going to call that breakpoint 3 evidence. And really, in the real world, your axles are typically spread on a regular 53-foot truck. They're only spread by about 4 feet. So if we can't isolate that it came from the front axle or the rear axle, we measure to a midpoint in between the two, and our equations are generally not that sensitive to variations in the tire distance of about this long or the skid distance. So it gives us a way to process the evidence that's useful and assigning it where it goes without trying to take steps or leaps too far and assign it to one axle or the other, when it's just as viable in terms of evidence and calculations to go to that midpoint. So that's what we're using, the odd numbers on the left, even numbers on the right, and if you have more axles up underneath your combination unit, or if you have multiple trailers or whatever, just carry that same numbering convention on, and just so we're all talking off the same sheet of music. Because as we go through these projects, we're going to talk about distances. Breakpoint 3, for instance, left a tire mark of whatever distance. So wanted you to have that convention, or that naming convention. So that's what we were talking about. What's displayed on the screen here is if we got 130 feet, we know it came from the left side of the trailer. We say breakpoint 3, left tire marks for a distance of 130 feet. And that gets us to the point where we're able to walk forward to do our calculations. So here is project number 1, speed project number 1. Should have that in your PDF handouts. Probably don't need to print it. You can just read it on screen and make some notes. And we're only going to answer the 3 questions down here in the bottom. And as with any word project, read through it, decide what it is that you need to know. The question that's posed to you is initial speed. And determine if there's a way that you can walk through this and just give that answer, not give partial answers or combined answers, but is there a way that we can answer that one and only question that we're posed? How fast was he going when he hit the brakes? So we can walk through this and get ourselves to a point where we can understand it all. So in this case, I think it's fairly straightforward without looking at measurements or calculations or anything. We have a trailer-only application. So it looks like the driver used the trolley brake, thought that he could slow down enough in response to what was in front of him, but in doing so ended up with a trailer swing, and so we end up with a trailer swing that pulls the truck around into a partial jackknife. So if we look through our evidence field, just based upon that quick look alone, we know that we're going to have to make some efficiency adjustments. So let's have that in mind. Let's just kind of as we're getting things out of our equation toolbox, we're going to need to correlate this efficiency and make sure that our factors that we use, our drag factors, are appropriate. And also we see that we're on two surfaces. If you look at the bottom of the page, you see there's some tire marking on the roadway prior to the departure on the shoulder, and that there's some grade on both surfaces. So again, we're going to have to account for that. So let's walk through this together, and you can do it in whatever order you want. Pause as you need, but these are just the way that I walk through it, and we'll see where that gets us. So the first thing that I feel like we probably ought to do is get a reasonable drag factor, starting at final rest, backing up through our evidence so we're on the shoulder. In this case, we had a drag sled pulled. The sled weighed 33 pounds. Our pull force was 18, and that gives us a F for the test of a 0.54. And so we can take that now, and we can adjust that. Remember, we have some grade. So we need to adjust. We have a 4% grade on the shoulder, a downhill 4% grade. So in order to get up to mu, where we can do any efficiency adjustment, we have to take that downhill grade out, bring it up to level, and that gets us to a 0.58. So then we can take our 0.58 and go into our F adjusted equation that we see in the bottom right there. And so we're given an efficiency for the trailer of 22.5%. And I think that based on some of the things we've looked at and through your brake force calculations, you'll see that that's not an unreasonable number for a trailer. So I think the ones that we did in the brake force projects all fell in the 0.2-ish sort of a range. So we're given 22.5% stated that way. Math-wise, we're going to have to use that as a decimal. So we have our 0.58 mu multiplied by our efficiency, and that gives us a 0.13. And then we're going to take the grade back out of it, minus the 0.04, which gets us to an F adjusted for the shoulder of 0.09. So we've accomplished one task there. Write that down and keep moving. And so staying on the shoulder, we're given some distances. We're given distances for brake point 3 and brake point 4, which are going to be our trailer axles. And we want to track the motion of that whole axle grouping. And so we're going to go to a point midway between all those axles, and that's going to be our imaginary point. So we're going to have to add and average those two. And so we get our brake point distances. Note that we're giving them out in feet and inches, and so we need to convert that into decimal feet. So whatever our inches are, divide by 12, and that gets us our decimal feet. And so we have our values, so we just add those two up, divide by 2, and we get our average distance for the shoulder of 217.99 feet. Now let's do the same thing. We've backed through the evidence field. We've got a distance and we've got an F for the shoulder. Let's do the same thing for the asphalt portion. Again, with a sled pull, we end up with a 0.63. Our grade is different. It's still a downhill grade of 3%. So our F test, adjusted to bring it to mu, is going to get us a 0.66. We can take that 0.66. We're still working with our 22.5% efficient trailer. So we can make our adjustment there. Now that we're at level, our 0.66 times our efficiency gets us to a 0.148, which is in essence a 0.15. It's easier to do that mathematically than carry 3 places. Minus our grade of a 0.03, and that gets us to an F adjusted for the asphalt. And you can see that I'm using subscript numbers here to try and keep track of these things. You can call it F1, F2, whatever it is, but we're going to get into some of these projects later on where we have multiple surfaces and different things leaving different marks in different places, and it can get somewhat confusing. So set your papers up so that you can manage this in its slices. It makes it a little bit easier. And our distance on the roadway, a little bit shorter, so we just do the same process. Add an average, brake point 3, brake point 4, and our average distance on the asphalt is 94.53 feet. So if our question was the initial speed, we know that we needed some distance, we needed some drag factors, we have those accomplished, and we can step into working some speed calculations. Now here is the preferred methodology, is that we know at final rest we're traveling at 0 miles per hour. And so we can use, we know that we're going to be combining some speeds as we go upstream, and we want to be careful to get to a point where we can identify and isolate specific discrete points in our evidence and be able to say that the initial speed was X, which is the only question that we're given, but through this method we're going to get also the speed at the time the trailer departed the roadway and went onto the shoulder. So our speed original from final rest is 0, so we just plug that in as a placeholder. We get 30 df with our shoulder distance and our shoulder f, and we find out that the segment on the shoulder was 24.26 miles per hour. Now we now have to count for the roadway, so we need to bring that 24 mile per hour figure over and do that equation one more time. Our speed original now becomes that 24.26 for the departure on the shoulder. We will square that and then bring in our roadway and roadway distance and our roadway drag factor. And so we do that, and then we have answered the question that we are at 30.47 or 30 miles per hour at the time we began seeing physical evidence on the roadway. So we've answered the 3 questions that we needed to have answered. We took a 2-step process to get to the speed answer. But there is another way. We can do a single equation, and here this is, where we can just get to that answer just once and not have to worry with that intermediate speed. And so you don't see this all that often, but when we're doing combined speeds in this manner, we're not doing kinetic energy quite yet, but when we're doing combined speeds in this manner, we're just working with chunks of 30 df. Everybody is familiar with that workhorse equation, 30 df. So in this case, we just take those chunks and combine it all together. So we got our the square root of 30 times the distance on the shoulder times the f on the shoulder, plus the distance on the asphalt times the f on the asphalt. And that gives us our same values. And if we work down through the equation, when we solve it, we get one answer that incorporates all the evidence, and we get exactly the same speed of 30.47 miles per hour. The remainder of the speed projects are very similar to this. Just read through them carefully and contact us if you have any questions on getting those worked out successfully. You have solution sheets in your PDFs as well.